teacher Neth, and welcome back to our general math class. Now that you know how to solve logarithmic equations using the properties and laws of logarithms, we will extend this to solving logarithmic inequalities. So let's begin. Solving a logarithmic inequality is just like solving a logarithmic equation in such a way that we may solve it using properties and laws of logarithms. Likewise, solving a logarithmic inequality is like solving an exponential inequality or equation in such a way that properties of inequality apply. One property of logarithmic inequality is that if b is greater than 0 but less than 1, then x sub 1 is less than x sub 2 if and only if logarithm of x sub 1 to the base b is greater than logarithm of x sub 2 to the base b. Another property is that if b is greater than 1, then x sub 1 is less than x sub 2 if and only if logarithm of x sub 1 to the base b is less than logarithm of x sub 2 to the base b. In addition, it may also be considered a property that the value of x in y equals logarithm of x to the base b is positive. This can be understood better from its exponential form x equals b to the y, where b is positive except for positive 1. Whatever the value of y is, negative, 0, or positive, integer or fraction, the value of its power, x, is always positive. Going back, x in y equals logarithm of x to the base b is always positive.
Example 1. Solve the logarithmic inequality logarithm of the binomial x plus 37 to the base 2 is less than logarithm of the binomial 4x minus a to the base 2. Since we are asked to solve for the value of x, then we should consider that the anti-logarithm is always positive. We should consider that because x is part of every anti-logarithm in this inequality. That is, x plus 37 is greater than 0, and at the same time, 4x minus a is also greater than 0. Then let us solve for the value of x in each of these two inequalities. Okay, next, we'll get x is greater than negative 37. That comes from adding negative 37 to both sides. When we add negative 37 to x plus 37, 37 minus 37 is 0, we'll be left with x. Then, to the other side, 0 plus negative 37 is negative 37. So that's why you get here the value of x, which is x is greater than negative 37. For the next inequality, what we did was we added positive a to both sides. So negative 8 plus 8 is 0. We'll get 4x. And then to its right side, 0 plus 8 is 8. So you have 4x is greater than 8. However, this is not yet the value of x because we still have here 4. The numerical coefficient of x is not yet 1. So let us simply divide both sides by 4 or multiply both sides by 4, and you'll get x is greater than 2. If you divide both sides by 4, that is 4x divided by 4 is x, and 8 divided by 4 is 2. So for the second inequality, this is the solution. Now, combining these two, we will be needing a number line. Let us locate negative 37 and positive 2. Then any negative number is to the right of any positive number, or is to the left of any positive number. So if negative 37 is here, 2 is somewhere here to the right of negative 37. And then since the first inequality, we consider this one because they are the same. Since x is greater than negative 37, that means it cannot be exactly negative 37. So we'll write here or place here an open circle. Then all numbers which are greater than negative 37 are the numbers to its right. So we'll be shading this part as well as the arrow to denote that even if the number line extends that will be part of the solution. For the next inequality, it tells that x is greater than positive 2. So all numbers greater than positive 2. Let's use another column. Since it cannot be equal to 2, then again we'll place here an open circle. And next, numbers greater than 2 are the numbers to its right. And since the shaded parts meet here or intersect here, then when you combine these two inequalities, that means the solution is x is greater than 2. All numbers greater than 2. Because if x is greater than 2, for sure, that is also greater than negative 37. Now, another thing we should consider is the property of the logarithmic inequality. And that is based on the value of b. Since b is greater than 1, in this case it is 2, then whatever the sign of the logarithmic inequality, this as a whole, the inequality symbol is less than, it will be retained even if we consider their anti-logarithms. That is, since the logarithm of x plus 37 to the base 2 is less than the logarithm of 4x minus 8 to the base 2, then the anti-logarithm x plus 37 is also less than the anti-logarithm 4x minus 8. So the inequality symbol is retained. That is if b is greater than 1. Okay, then solving for x, we'll combine x with 4x and then 37 with negative 8. Okay, that is, we add positive 8 to both sides in order to eliminate 8 in the right side. Negative 8 plus 8 is 0. Here, we'll have 37 plus 8. And then to combine all terms with x, we will add negative x to both sides. So in the left side, you'll get x minus x is 0. And in the right side, it will be 4x minus x. Combining them, we'll get 45 is less than 3x. By dividing both sides by 3 or multiplying both sides by 1/3, we will get 15 is less than x. 15 is less than x is the same as x is greater than 15. So by reflexive property, we have x is greater than 15. So this is another solution or values of x we should consider. Combining these two now, I'll use another color. X is greater than 2 and x is greater than 15. Let us locate them again in a number line. Two is less than 15, then 2 will be to the left of 15. The first inequality tells us that x is greater than 2. So all numbers to the right of 2, but not exactly 2. So again, we'll have an open circle, and then all these numbers to its right, plus the arrow. Another pen. For the second inequality, all numbers greater than 15. So it cannot be 15, so open hole, and then all numbers to its right. Now, since the shaded parts intersect here, then that means the solution set will be from 15 exclusive because it cannot be equal to 15, and that's why we have here open parentheses. So 15 exclusive to positive infinity. Okay, example 2. Find x in logarithm of the binomial x plus 2 to the 1/3 is greater than or equal to logarithm of 4 to the 1/3. Again, since the anti-logarithm is greater than 0, then we should consider that x plus 2 is greater than 0. And that means by adding negative 2 to both sides, x should be greater than negative 2. Next, another thing that we should consider in solving for this logarithmic inequality is the property of logarithmic inequality, which is based on the value of b. Since b is 1/3, which is between 0 and 1, then that means the inequality symbol will be reversed when we consider their anti-logarithms. That is, given this inequality, when you compare their anti-logarithms, the inequality symbol will be reversed. That is, x plus 2 is less than or equal to 4. That happens if b is between 0 and 1, which in this case is 1/3. Okay, going back, by solving for the value of x, we'll add -2 to both sides, and you'll get x is less than or equal to 2. Because when you add -2 here, 2 minus 2 is 0, you'll be left with x. Here, 4 plus -2 or 4 minus 2 is 2. So x is less than or equal to 2. Now, combining these two solutions, locating them in a number line will help us determine the correct solution set. One is -2, the other is +2. The negative number is to the left of the positive one. So +2. The first inequality, the green inequality, tells us that x is greater than -2. So that means it cannot be exactly 2. So we'll have an open circle here. Draw an open circle. Okay. And then all the values of x which are greater than -2. And those numbers are located to the right of -2. And all other numbers. Let us shade also the arrow. Next, for the second inequality, it tells us that x is greater than or equal to +2. Since x can be equal to +2, then we'll have here a shaded circle. And then x is less than. So numbers which are less than +2 are the numbers to the left of +2. So these are the numbers to the left of +2. Okay, where do the shaded parts meet? Here, in this part. Therefore, the solution set is -2 exclusive to +2 inclusive, because it includes +2 but it does not include -2. All those numbers between them and +2. Example 3. Solve logarithm of the binomial x plus 6 to the base 11 is greater than 1 but less than 2. We are asked to solve for the value of x. It is part of the anti-logarithm. So we will consider the fact that every anti-logarithm is positive. That is, x plus 6 is greater than 0. And by adding -6 to both sides, we'll get the value of x. The solution is x is greater than -6. Okay, we will consider this solution later. Next, another thing we should consider is the property of logarithmic inequality. Okay, we will form here two logarithmic inequalities. This will be the first, and the second is this. Okay, going back to the first, which is 1 is less than logarithm of the binomial x plus 6 to the base 11. In order for us to solve this inequality, we will not simply transpose +1 to the other side. will not be able to solve for the value of x because this is a logarithm. When you are dealing with logarithm and it's a logarithmic inequality, you will express this 1 or the left side of the inequality in terms of logarithm also with base 11 also, with the same base. We have learned from the properties of logarithm that a logarithm is equal to 1 if the anti-logarithm and the base are the same. Okay, what we are trying to drive at is logarithm of 11 to the base 11 is also 1, or 1 may be expressed in terms of this logarithm. We have learned this in properties of logarithms, that if the anti-logarithm and base are equal, then the value of the whole logarithm is equal to 1. Okay, why 11? Because we want to express 1 in terms of logarithm with the same base. If this happens to be 12, then this will be 12 and this is also 12. But since it's 11, so its logarithm of 11 to the base 11 equals 1. Okay, now that both sides of the inequality are logarithms to the base 11, then we may now consider the value of b. Since the value of b is 11, this is b, the base, and it is greater than 1, then we'll follow again the property of logarithmic inequality that tells that the inequality symbol will be retained. That is, since the given is logarithm of 11 to the base 11 is less than logarithm of x plus 6 to the base 11, then when we consider these anti-logarithms only, the inequality symbol will be retained. That is, 11 is less than x plus 6. And from here, we'll be able to solve for x by using or by adding negative 6 to both sides. And then we know that this is 5 is less than x. Simply put, that is x is greater than 5. So another solution we will consider later. Okay, we have encircled here the next logarithmic inequality. So we have logarithm of x plus 6 to the base 11 is less than 2. Like what we did with the first inequality where we express 1, the constant term, in terms of the logarithm to the same base, we'll also express 2 in terms of logarithm to the base 11. And that is 2 times logarithm of 11 to the base 11. Because since the value of this is 1, then this will be reduced to 2 times 1 or still 2. So they are just equal. Okay, now that we have expressed this in terms of logarithm to the same base, like the left side, then by power law, we know that this factor will be the exponent of 12. That is, logarithm of x plus 6 to the base 11 is less than logarithm of 11 squared to the base 11. Okay, let us simplify this part. We know that 11 squared is 121. Okay, since both left and right sides of the inequality are expressed as logarithms with the same bases, then we'll now take a look at the value of b, which is 11, which again is greater than positive 1. Again, if b is greater than positive 1, then the value of or the symbol of the inequality will be retained. Since logarithm of x plus 6 to the base 11 is less than logarithm of 121 to the base 11, then x plus 6, this anti-logarithm, is also less than 121, the other anti-logarithm. So the inequality symbol is retained since b is greater than 1. Now, solving for x, we have x is less than 121 minus 6 or 115. Another value of x or another solution. So in a number line, let us locate these three numbers. We have here negative 6, positive 5, and positive 115. So negative 6 will be the leftmost number among these three. Negative 6. And then we'll have positive 5, and 115 will be the rightmost. Now, we arrange from least to greatest. Now, the green inequality tells us that the value of x is any number which is greater than negative 6. So it cannot be 6. So there will be a hole here. And all the numbers which are greater than it. These are all those numbers. Next. This inequality tells us that x is any number which is greater than 5 but not equal to 5. So we'll again have an open circle, and then we'll shade all the numbers. These are the solutions. All the numbers greater than or to the right of 5. And for the last equation, we have x is greater than or is less than 115. So that means it cannot be 115. That's why we'll again have an open circle, or 115, and then all numbers which are less than it, or all the numbers to its left. Okay, where do the three solutions meet? If you notice, they meet at this part or area. From 5 exclusive to 115 exclusive. Because we have here an open circle, so 5 is not also included. 5 exclusive to 115 exclusive. Meaning the solution are those parts, or is the part which is common to the three solutions. And this is that part. From 5 exclusive to 115 exclusive.
To solve a logarithmic inequality is to take some considerations. By saying this, I mean one must bear in mind some properties in solving a logarithmic inequality. Until next time!